probably pick them just because we spend more money on them. Yeah, so we just get better properties. Anyway, let me all right, so last time we were talking about diodes. Do, do, do. And this time we want to start talking about BJTs. So, and as was mentioned at the beginning, just, there's a lot more in the logic families. And at some point here, I'll have to put in some stuff on how a BJT is built, I guess. But we'll do a little bit of that right now. So right now we've got, we've had a P and an N. All right? What's P? What's positive, negative? What's positive, negative? It's the charge in there. The carrier charge, yeah. It is electrically neutral. Okay, you can this PN. Very good. The boundary creates a depletion zone, which means those charge carriers kind of, the electron drop into the hole and boom, we get a big number. Right? Which way will things flow? Right? So we're usually talking conventional currents, which I know is annoying as heck, because we're all trying to generate functions, but that's not what we do. So conventional current, which way does it flow? P to N. Or what? P to N. P to N, yes. Okay. It's the stupidest thing, it ain't right, but I learned it very early on. It's the direction you're peeing. Yeah, I did too when it was first told to me in the 80s, but I guarantee you will never forget it. Okay, it only flows P to N. Like if we're talking positive, i.e. conventional current, which we know is wrong. It should be electrons, but then it would go the opposite direction. Right? So, is what it is. That's how at least one easy way to remember. So remember, it goes this way, right? If you're going the other way, you see a wall, hence you get your diode symbol. Sorry. Yeah, I wish they put the light so I could tell when it was in frame and not. All right. Now, we want to go the next level up. What if I were to, for instance, put another N region here? All right. So I have these kind of two depletion zones. All right. And we know from this P to N it makes this diode. So it's got to do the same thing here, orientation. Right? So I end up with something that looks like this, right? So I theoretically can have a wire in the middle if I want it. Now, how is this even remotely useful? To one side will start flowing. Yeah, see, this is the thing. Remember that these depletion zones are that there's not enough carriers. So what if I just took one of these and I forward biased it? Right? So I put a forward bias on this. So now this depletion zone goes away. So it's now flowing. That means there's more than enough charge carriers to remove the depletion zone on this side, which means some of them come over here and remove this depletion zone also, right? Because those charge is going to spread, right? So it's going to go in. Once you start something flowing, you've got more than enough charge carriers, the other depletion zone is gone, and what do you now have? That's a wire, right? In essence now, this is a wire. Make sense? Because remember, the basic idea is if I can cause this to flow here, there's charge carriers coming in, so they're going to go all over the place, right? There's more, once I get past that 0.7 volt, I've got so many charge carriers, they're all over the place, right? Well, what was the happening before? I had depletions on both sides. Those charge carriers were, and we're going to repeat the depletions. Then we can also do this in terms of the energy levels, and you can look at it and see their rates and all. But I don't think you'll have too much trouble just on, this is a pretty straightforward, simple idea. The charge carriers come in and it just fills. Now everything is conducting. So it's as if I just had a big. Now, what would happen if we started lowering that forward bias? It gets closer and closer to a depletion zone. When it's way, I got tons of charge carriers. It just flows very easy. Right? As I lower it, it gets closer and closer. Right? There's less and less charge carriers, which means it doesn't flow quite as easy. And eventually, if I put it too low, it just stops. So I see it happen something that looks like easy flowing, and then it slows down and eventually stops. It's actually a very resistance, isn't it? But it's a resistance that's, on the area around directly doing the controlling. It's on that other area that I see the resistance. So it's not the resistance here, it's the resistance over there. Now the word for kind of over there is trans, cross. So this is what we're seeing is a trans resistance. And then you say that really quick, you get a transistor. Oh, that's where your name came from. Okay? So it is when I'm using one leg, one of these diodes will cause both of them to disappear in essence. And I can, by how much charge carrier, I can make it really easy to flow or hard to flow on that other side. Because all I'm doing is creating the charge carriers that allows something else to make the flow. So it can be many times larger because I'm just providing a connection by doing this. It is not possible for the other side to provide a connection because it's got the back-to-back diodes. Whichever way I did it, it would have mapped it up. So you can't force it the other way. I can only kind of start it going this way, and then it's all based on what you pump into it. And that allows me to also do amplification. And because basically whatever I do is going to get amplified on the other side because I can put what I want. When we realize we get that kind of beta value, everybody's gone through electronics, right? So typically that's like 99 or so. It's typically used as an input there. But as far as we're concerned, we have 2 orders of magnitude, plenty big, really easy to make this on and off. Now, we're not going to care too much about straight amplification. We want to just flame things on and flame. We're going to go kind of hard on home because we're going to use this as a switch. And this now allows us to have an electrical switch. Now, there are ways you can make electromechanical switches, but this is a huge advantage to have purely electrical. Anybody know what the electromechanical switch is? A relay, very good. Yeah, there's a couple of varieties. I mean, there's a basic relay, which is like a coil, and there's a magnet. You charge the coil up, and it basically pulls it shut, and it makes a physical connection to it. That's a basic one. There are reed relays, which, essentially a thin wire that uses an effector nearby to pull it close. There's a couple of ways you can do these. There are some problems with these. Most notably, if you ever have to deal with them, they cause a lot of jumps. Anytime there's a physical connection that's being closed as opposed to an electrical, when it closes, so imagine this is my inductor here, this is the switch. When this one creates a field and pulls it shut, it's not going to just slam and stay there, right? It's going to go. It's going to bounce, right? I mean, it might be tiny, unless you've got the world's greatest magnet, right? Or filming, and they discovered how challenging this was. Like in Lord of the Rings, you ever see that scene where they drop the ring of blood, right? They had to stick a giant magnet on the other side and make a basic orange which called thud against it. But if you looked at it small enough, there's always vibrations that are happening as a result of this. The problem is for us electrically, that causes on spikes. I mean, and that's really problematic. Now we got to debalance the switch and all kinds of things. It's also slower, turning on and off. So there's a lot of these mechanical problems that kind of come on, and think of the power you're having to dissipate. So for building logic gates, theoretically, you could do computers out of relays. That's what they did in the 40s. If you heard about them, the old ENIAC, right, the electrical, all that. So they had the early starts of these in there, but it really was impractical and very rapidly it switched out. Anybody know who was one of the big founders of the whole transistor idea? Kind of relates to us here. They was a little bit of that. Yes. So one of the PI who was foundational builder this was Gordon Teal. He was a Baylor chemist or a student who graduated chemistry. That's why we have Teal Hall, because he was one of the guys who started the transistor industry. So that's kind of your little bits of Baylor history on them too. All right, we feel good with transistors and the idea, right? Their advantage over mechanical ones, mainly speed, you don't get those stupid bounces, stuff like that, lower power, things of that sort. Much, much smaller also. They're also more reliable. You can get oxide layers building up inside those other things. So there are some advantages that happen to a relay, but it's only really, really high power. So there's only been one time in my career I've had to heavily deal with relays. And for a little while, I worked at Northrop Grumman, and when we were launching basically missiles from aircraft, we had to use relays because it was so high current flow. There was nothing at the time that could easily handle it, so we used relays to pass that to it. But unless you're dealing with something like that, right? If you're dealing with super crazy high amounts of power going through, a relay has an advantage, but otherwise not too useful. All right, so now we've got this idea of at least a transresistor or transistor. Let me mention a couple ways we can build this, and then we'll talk about what we can do with it. Usually we don't build it like this, right? And, making something and going N, P, N. That's actually fairly hard to fabricate. Because what are you doing? Chopping them up and sticking them together and got air gaps. Just gets ugly, right? So it's easier to actually build these. Anybody ever looked at how you have to build something in silicon? Yeah, you have to do it kind of layer by layer. What does that even mean? Right? So usually there's a couple ways you could actually dope materials. The easiest way but to get a constant thing is to just, when you're actually forming the silicon rod, right, and you get a molten silicon and you pull it out like a grain seed, and you'll get this, initially it's a cone and then you get a set rate, and then it's pretty close to a cylinder after that. If you actually have the dopant in there, when things are molten, it diffuses really well. You get an amazingly even blend. So whatever is the background dopant value you want for this, you'll often do, as whatever that is. So let's say, for instance, I might make the background be N type. So I would actually, at that point, just get a silicon wafer, which is you just pull that cylinder on and then you slice them. Now you have a wafer of this, and I could make it, for instance, N-type. Pretty nice, even to it. And then let's say I wanted to diffuse P-type into this. There's a series of what we would do this. We would put on a material on top of this that we would layer. And this material is usually a photoresist, which means you can, by emitting certain light onto it, you can actually change its properties. And so what we would often do is then come in and separate. Like let's say I wanted to make a P well in here, right? I would have this center part exposed differently, right? One gets light, one doesn't get light, right? The one that gets light is going to kind of be hardened off. And then I could do an acid wash that will only affect one of the two. And I basically wash away. So let's say I wash away this middle zone. Now, this is protected, and this part in the middle, there's no longer anything there. So there's no problem. I can expose things. Now what I would do is I could, for instance, do CVD or some other type of a process where I basically expose P dopant on the air, pressure, time, let it go, and it diffuses. So diffusion is the next typical step that goes in, and we create a well. And it actually slightly undercuts this, so you have to count that. But let's say we get P dopant that now comes in. So now, since I've allowed that P material to diffuse in, I've made a P material well inside there. Now I take a different thing and I wash off the rest of this. This is now all gone, and I just have my material here. Then I could do the same exact trick again. I could do a photoresist layer. I'm just going to show it in a slightly different color, whatever I picked up. Okay, I picked up red, right? And let's say in this case now I would do another mask, usually with light. So this is one of those tricks with shaped masks of the layouts and the shine light. One of the big areas is how do you actually find light? You got to get the right wavelength to be able to expose it, right? So we're getting down to things that are nanometer scale, which means you need a fairly high energy photon. So I've got to find stuff that reacts in that range. This is why materials become such a big deal, right? Because how do I make the reactants? How do I do all the rest of this? And remember, it's got to be stuff that's right on that kind of top layer of the periodic chart to do this, or chemical compounds that use those, so I don't accidentally get some pollutant that gets ruined everything. But let's say I come in and again, I make two wells in here, right? And I get my resist, and it covers these. I remove the parts in the middle, and then I allow, again, this time N-type material in the air, so I get two more little N wells, and I remove it again. See how I can kind of just, in a series of actions on here, I can do this. And then if I want to build up another layer, I don't have to put any resist on it. I can actually spin on material and things of that sort that has a particular dopant. And I can add a new layer to this. So now you might wonder why did I start with N? Because if you notice here, see the two N's at the top and the P? Notice if you look between them, I've got an NPN. See them right here? NPN. That is the transistor right there. Why would I want this extra thing all steady distance in an N-type material? Isolated? Yeah, exactly. It prevents stuff from flowing, because I'm going to build a whole bunch of other transistors out here too. So if I put this inside, again, an opposing material, you in essence have a shield around it in some sense. It prevents leakage currents and other things to other transistors. So I don't accidentally turn on other transistors. So it's all about isolation at that point. Does that make sense? So this is much more what you're actually looking like when you're building these. And then I'll hook them up to be able to achieve this end. Now, I want you to also notice something else with this, right? So that's kind of basically how you build them. So remember our symbol here? We said it looks like this. That's kind of awkward to draw, though, isn't it? And we said we're really using this one here, for instance, to be our control egg. So I don't want you to use the other one, so I'm not going to draw. So this center part here, I'm going to keep them. I care about this diode, so I'm going to draw it. And I don't want you to use that one, so I'm not. There's your BJT transistor. Yay! So now you know what it is. You can also look at that one and pretty easily see that's the control leg. And it tells you the arrow's pointing that way, so it's got to be the PN junction that way. So it tells you it must be an NPN because the middle point is P. So the NPN has to be N also. Yay! So now you can look at it and immediately tell what it is because you remember what a diode is. All right. Now, what if instead of just having one of these wells, what if I had two of them on one side? Couldn't I have just made something that looks like two? So yeah, and, and here. So couldn't I just do something like that? Anything wrong with it? Because there's, no, it's actually really darn useful. We do this. This is actually a really common way, right? So we care whether this is a great way to actually make logic. So think about it. Remember last time we had our little diode logic stuff? Anybody remember these ones? And something going up to power. If either of these go to zero, then this flows, that pulls down to zero. Right? If both of these are high, nothing flows, so they're in essence not there, and it gets pulled up by that resistor. And that was an AND gate. Well, why do I need two diodes? Right? Both of these are acting as controls for this junction. That's exactly what this is doing. I've got two ones acting like a control. So this can just be drawn as I've got two control legs. So if I want to build this at that junction area, I need a resistor going up to power. There you go. Two diodes, there they are, and there's my output. Now think about it. This is some A, this is some B, this is some C, right? So let's imagine A, B, C is my output. So we've got, I'm just going to use 0 and 1, by which 0 I mean ground and 1 I mean high voltage. High enough to actually open, you know, see how to do it. Whatever this voltage up here high is, that's 1. This is called positive logic, fairly standard convention. So I guess I should put there actually. All right. So if one of these goes to 0, right? If I put a 0 on one of these, remember we get current flowing through here, which means its current's going to go all over and remove all of those. Now, if you've already got a high voltage over here, then there's nothing to do. Nothing's trying to flow there. Right? But this one being removed means now, right, I've got this all flowing here, and I've got a weak one because it's hooked to a resistor. So it'll limit what it can do. And I've got a stronger 0 over here, so it's going to pull this one down. So I get a 0. In truth, it'll probably be a little bit above 0, but it'll probably be, it'll probably less than 1 volt, but probably getting close to it, but still low enough that we can count it as a 0. So now in one gate, I've built an AND gate. This is kind of a nice feature. I can do it very easily. There are other ways to do this, but this is a good first simple. So far, so good? So if I get a 0 on here, we get a 0 here. And that same thing, it doesn't matter which gate it's on. So if I got any zeros, I got a 0. But if they're both 1, nothing flows. So C is in essence going to get pulled up. Because it's at most going to be, since this technically also is a diode, it at most can be 7/10 of a volt. So it'll get pulled high. If nothing's flowing from here and nobody's trying to insert something on this, it'll get pulled to 7/10 of a volt less than. Does that make sense? All right, because if there's nothing here, if these are both ones, they're in essence not doing anything. So this is just a diode, and that's once it's already mostly in forward bias. So, yeah. This one cannot be less than high minus 0.7. Otherwise, that diode opens up and flows into actually. Okay. So then, therefore, this becomes a 1. So that's kind of cool in a single transistor to be able to do that. Now, the problem is most of these are not particularly strong. Right? Because remember, my output, if it's a 0 on one of the inputs, the output, just like with diode logic, is controlled by that original signal. But we just use some of it to open the gate, so it won't be quite as good of a value. It's not as strong, right? The less power and voltage has decreased a little bit because we used it. Right? So it's not as good as the original signal. Right? But we don't want that. Right? This is still a logic function for us, very cool. Signals we could just like with diodes. But I'm not limited to just doing one configuration. Right? And I could decide, for instance, to just put an amplifier on this now. And we know transistors do a good job doing an amplifier. So let's consider one easy way I could do an amplifier. You're good with this? Because now we in essence have a gate, right? That's an AND gate, right? But we said it's not a great AND gate. The output's a little bit weak. So our next thought is, what if we amplify? So how can I build a simple amplifier? What's the simplest amplifier I can build with a transistor? Can I build it with just one transistor? Single transistor amplifiers. I'm not saying they're the best amplifier in the world, but they certainly are. So let's consider another configuration here. Right? So I've got an output here. I'm going to call this one A. I'm going to call this one B. Now, this A is referenced to something, so I kind of want a ground. Because that's going to give me an easy reference for this, because that's my control lane. That's where the diode is. And remember, right, I either have to have a high or a low on one side. Before I had the high here, so I could then have variable. In order to forward bias, I've got to have ground on this side, because now I want the input coming here. Does that make sense? All right. Now, if A goes high, I say like 5 volts, what happens? It goes high. Yeah, this is going to turn on. How hard is it going to turn on? 4 volts. Yeah, 4 volts. So that's 11 volts on basically 0 resistance. So you're going to get a ludicrous amount of current, and what's going to happen? It's going to burn out. Let the magic smoke out, and it's all over with. So I've got to make sure I'm spot that current. How can you spot current?
You could transition for current laws. What you could do is
Okay, so there's a couple ways. The easiest is a resistor. So if I want to use a resistor, where I've got two spots I could use it, right? I'm trying to stop this current flow. So I could either put the resistor here or here. Those are my two choices. Which would I prefer? Okay, so, right, remember, if this flows here, that means this opens up. Yes. You don't want both of these paths affected. And in particular, if I put it here, right, then yes, it will protect, but I've got current flowing through this. Current flowing through a resistor causes voltage drop. So that's going to lift this to above zero. Do you want that? I'm trying to volunteer, right? So I want the zero to be as low as possible because it's going to be like because this B is my output. Not something raising my zero voltage up on the ground. So I don't want this spot. So that's why you always see the resistor here. All right, because it will protect this, but it will not cause a change of your. Now remember, a little bit of current flowing in this control leg causes a huge potential amount, right? So that's it's very, very low resistance, right? Easy flow. Low resistance means that in essence you get pulled down to that ground really hard. So this gives me a very good zero. So we go, yeah, that's what we want. We get really good zero. So we like this. Right? So now we've got, let me neaten up my picture a bit. A goes through a resistor. Actually, let me just draw a resistor there. And this resistor is for current limit. And remember, I just need some current flowing here. It doesn't have to be strong at all. As long as you get over 7 volts, more than that, right? Even if it's coming in weak at 4 volts or 3.5 volts, even if it's 2 volts, more than enough for that 7-volt drop plus volts. Remember, a tenth of a volt on this is enough to accelerate that electron to be traveling thousands of miles an hour. It's ridiculous. So there's electrons are really, really light. It doesn't take a lot of voltage to get those suckers flying once they're up in the conduction band. So we've achieved that with the 0.7 volts. So the resistor that's in that spot just stops us from burning things out. All right, now we've got our output B. So let's consider two possibilities with A. All right, now if A is 0 or A could be 1. And we just said if A was 1, this turns on, so this connects. So what happens to B? If A is 1. Yeah, it gets pulled down to 0 for B. All right, does that make sense? So A is on, current flows on the control leg. So the base to emitter is base to, and you've got your collector emitter one will now turn on, right? Very low resistance, pulls it down, boom, goes to 0. What happens if A is 0? Does anything flow here? No. So nothing flows here. So we can jokingly do what's called the Watergate method. You just cover up. Okay? It's an old joke. It's old when I was told it. But it's memorable. Like many of these stupid old jokes are very memorable, stupid old jokes. But it will remind you what to do. Right? If nothing's flowing there, just, in essence, remove it. They're disconnected. So what does B become then? Yeah, it's very good. So we can now say we don't know what's hooked up to it at this moment because all we've done is unhooked it from everything we have. So this is, in essence, what we would call Z, high impedance. Okay? Now, if I were to put a pull-up resistor on B, it wouldn't affect the ground, would it? No, not as long as you pick a decent, over like 500 ohms, you'll have no problems, right? But if it's disconnected, what's going to happen? When you've got a voltage up there, so that becomes a 1. So I have an option, right? I'll put a blue for my option. I could put another resistor going to power, right? Which this would be a pull-up resistor.
Technically pull to ground, that would not be logic anymore.
Yeah, that would just be straight 0 out. Right? Now, let's think about this one as far as it goes. What does that look like? Let's say, for instance, I put the pull-up resistor. Z becomes 1. So what is this?
This is a,
It's an inverter, but how much current and how good is the voltage coming out of this?
voltage coming out of this, what you said, voltage.
Yeah, so it's strong. It's coming from the source just through a resistor to limit how much flow there is. So this is now strong. It's been amplified. So this is an inverting amplifier. Yay! All right. So, cool. We've got an inverting amplifier state. So what would happen if I took my AND gate from here? All right. Take this. And I've got a resistor that is going to power. And I could put a resistor here if I so choose. We often don't because it actually has another resistor here to protect it, so who cares? But I'll draw it just for the sake of argument. So I've got A, B, and a C output. Okay. Now we can combine these, right? I've got a little middle point here, D, if you want to think about it. And we know that we basically get D is equal to A and B. Right? And we know that C, our output, is equal to not D. Right? I should put my pull-up resistor for this one also because I do it on the first one. Right? So that means that if I put this together, C is equal to A and B knotted, which is yes, it's a universal gate. Yay! Why do you call it a universal gate?
Because we can make any kind of logic.
How do you know you can make any logic with it?
Using absolute you said it's digital logic, but
Well, that's true, and I think you did learn that, right?
Yeah.
Hopefully you also knew why it was true.
it's true because we can it's fascinating. Like you can think the two words like and okay. Or
So yes, you've got a good idea here. Now, if you do that, you'd have to exhaustively prove them, just doing cascading. Let me give you a shortcut to see why this must be true. What's a canonical form? We love these, right? So we always were trying to write things in canonical form. Hopefully when you went to digital object. We had two of them. Sum of products or the sums. Now, this is the neat thing with these things. I can write anything. We know it's canonical form. I can write anything as a sum of products. It's just one of the basic rules, which just involves, you've got a, if you do the sum of products are ands. So I can have any combination of these ands that I want summed together. Now, if I have a NAND gate, we know NAND gates there's an equivalent form, I call them the Morgans. So we can put a NAND gate into an AND gate with inverted inputs. So we know that this, if you remember, is the equivalent of you flip the inputs, you flip the gate, and you flip the output. So this has to be this. So it's an inverted OR one. So I could therefore take, if I did a NAND gate into a NAND gate, I could do the first one in this form.
We can't see it.
I could do the first one kind of like this, and I could use that as the input into one gate of the next.
So the inverted.
And I have some other one, let's say C and D knotted. That'd be another NAND gate. Right? Or whatever else. You can make C and D whatever the heck you like. I can then run these two as inputs into here, which I would have an OR, and I would negate the inputs, and that's my output. Double negation goes away. All right? So I could have, this could be A and B, and this could be not A, B. You pick one of those inputs. So you can, essentially, we've shown that some product form is the equivalent of an AND gate into an AND gate. That's some product form. But anything can be written as some product form. So therefore, anything can be done by two layers of AND gates. Because we just showed the NAND gate is the equivalent of that canonical form. So the other universal gate was the NOR gate, which turns out to be the other one, the product of sums. And you can just show that it is also biased to Morgan, the exact equivalent of it. So it's an easy way to show. You can literally build anything out of these if you want, just two layers of either NAND or NOR. Anybody know why we use NAND gates more than NOR gates?
Because they're easy to design.
So they're actually pretty similar on the design area most of the time. Because it's just reversing, right? It turns out, NAND gates, notice we built this with all NPMs. Guess what would have happened if I picked PNPs? NOR gates would be the natural thing that flows out. Right? So now how good a NAND gate or how good a NOR gate is dependent on the underlying transistor. So which is better? NPN or PNP?
NPN.
Right? NPN is slightly better. Why?
Because it holds the.
It's slightly faster because we're mainly using electrons. Where when you do PNPs, you're mainly using holes, and holes is a little bit slower than electrons because it's like an electron with some extra steps. So it's just, there's a slight advantage in PNPs. Now, there are some cases where PNPs, and we'll take a look at some, right? There are some cases where PNPs actually become quite useful, right? And it's nice to know that. But for the most part, it's better to build everything on one type of transistor because it's easier when you're building them. Remember when we did those build-up layers? At the same time, in different parts of the chip, you could be building tons of these. So it's a lot easier if you're building them and you're putting N everywhere, and then you're putting P everywhere. So if you're building the same type of transistor, then you're going to be putting the same stuff in the same spot at the same time if you're all doing NPNs, or you're all doing PNPs. So it's better to do all of one transistor type if you can do it. Yeah, that's it. I mean, that's really how you build these things, right? And why there's a slight advantage to NPNs. Okay. Now, we also notice NPNs do a pretty good job switching around. So just keep that one in mind. Okay. So we've now seen that we can start out with these and we can build a simple transistor. Now, these inverting amplifiers do have some not so nice properties. There is a little bit, I mean, they do give you decent power. They do have some limitations. They're a little bit, this is actually pretty slow on the switch, relatively speaking, with the resistor. You do get some areas with the resistance of the output and how much current you can source and stuff like that. So it does have some limits. So that's going to give us to a little bit better of an area. But for a simple first thing, we're in good shape with this. Now, this is kind of like your standard TTL setup. I could omit this. What would happen if I omitted that? Yeah, I either give you zeros or I give you high impedance. So anybody ever hear of open collector output? All right, so some have, some haven't. So remember, collector, base, emitter, right? So if I don't put that resistor on there, the collector has nothing on it. So the collector, when you output it, is at Z, which is an open in your circuit. So open collector output means there is no resistor pulling you up. So far, so good? Okay. Now, why on earth would I ever want to do? Well, here's why. Imagine I had a whole bunch of these. Right? And remember, the second this has to actually flow, like this disappears, current is going this way. Right? Now, what would happen if down the line, right, I had two of these feeding into another one? Because we've already shown cascading these would make sense. Well, then I'd have all this current flowing into one, the next stage, right? And there's more out there, right? But I'd have all this current flowing into one, and I'd have a duplicate flowing all its current in here. So I've just doubled the amount of current flowing into my circuit. What would be three input gate? How much current would I have? Three inputs, potentially. See where I can start building up pretty crazy, pretty quick here? Right? Pretty soon you're going to get a ridiculous amount of current flowing in as you start adding more and more gates. And do we want more gates than just two? Well, it'd be nice, right? I mean, think about some of your logics that you built, right? So if I were building like some large, complicated circuit, and I could have a 4 or an 8 or a 16 input AND gate, that could help me calculate some things fairly quickly without cascading a bunch of logic. Remember, every gate adds latency. So if you give me more inputs and I can in one transistor calculate your whole thing, that's going to be fast, low latency. We like low latency, right? That gives you quicker circuits. But your quicker circuit means potentially a lot more current coming in. And a lot more current coming in, what happens if I get too much current? Heats up, let the magic smoke out, it's all done. Right? We don't like that. So we could say, for instance, there could be a problem here. Right? So one of which is, I'd ideally not like too much current line.
So very high, you have a high impedance instead of limiting out the current because it's not all.
Because there's no current being supplied. That device either gives you a ground or it gives you a not connected. You have to hook something else outside to give you the motor. Because remember, in our logic chart right up here, without that resistor in here, you either get a 0 or a Z coming out. Z means nothing, it's disconnected. Right? Now, that means I'm not ever supplying power. Right? Now, the fact that I supply a ground means I have to think, like if you supply power, I potentially have to think it through my transistor. So that's, I could potentially have to put going back in to make sure I can handle that. But you have to do that anyway. Okay? But on the next side, right, I've got something that's not actually having any power, and I can control that power elsewhere. On top of it, I could take two of these gates and wire them together. Since neither one provides power, I can't get a short accidentally. Okay? This is what's called wired logic. If you have a Z output, you can hook multiple gates together to build an effectively larger gate. You just hook little components together, and they just supply zeros, and when they supply a Z, if all of them supply a Z, you will get a high output with whatever you supply your power to. And you cannot possibly generate a problem with it because none of them supply power. So there's no way to short circuit if one's on and one's off. Right? That does mean externally you have to supply power. So for instance, a pull-up resistor. Now, that particular feature, no shorts, makes this actually still used. This is one of the times that you can still see this style of logic being used. Have you got an idea where you might want some open-ended logic thing where some things can be disconnected or connected and they can't possibly short?
Yes, the side, a thermal table.
Yeah, or what would happen if somebody missed, somebody did a bad job on their design, and if you didn't do this, you'd get a short. That'd be bad, right? Right? Who is the easiest to make a mistake person in the entire world? Students. Close. Users. This was taught on early. Assume your user is what they used to call the minimal man, right? Which was like a joke. Imagine the most error-prone person you could ever think of, right? So I would always pick. I had my roommate through college was an English major. I can, if anybody could break something by doing something wrong, it was him, right? So he was my minimal man. And I just assumed if I could make something that was brain-proof, it was probably going to focus. Okay? Well, that's the same thing here. Well, what if the person doing your logic function hookup is your user? Well, they are when they plug in a USB or any other peripheral. And you've got lots of things that might want to talk, and you don't want them to plug it in and burn something out by getting a short across that bus line. So generally speaking, you're going to put an open something output. So each device only supplies grounds, and there is a bus master, which is the only thing allowed to pull up and supply power. If there's only one thing supplying power, you cannot get a short, because that thing just protects its current limit and it's done. So this open collector idea was the first way buses were built. And that basic idea is still needed on a bus today. However you do it, you can do a similar thing with FETs, and we'll talk about that later too. But it makes sense here as a first intro. So that's the other reason it came in. You could, number one, do wired logic, so you can make bigger gates by hooking them together. But you could also make buses and make it such that somebody plugging a device in that couldn't get shocked. We generally do not want people to plug things in and large currents might go and damage the device that they just plugged in and give them a shock or whatever else. That's not safe. So there is a benefit for leaving that off. Then it gets handled by the bus master and you're done. Make sense? So if you ever wonder why on buses we only talk about pulling down, right, things of that sort, your bus should either, each device should either be one hookup or a zero hookup. And they should all either supply ones or zeros. and the bus master should be messy. So the master of the bus controls whatever that, whatever the missing quantity. In our case, if you were doing PNPs, then you do it the other way. Make sense? And you might still stuff. So understanding it is important. All right, so we've got these. Let's say that I don't want to supply power here, but I want to have a better output. This gets to be what we're going to call total. So now we're going to, in essence, do basically a push-pull type system. I want a separate thing to switch power and another one to switch ground. So we're going to take this area here and let's consider the switching ground. Well, I already kind of know how to do that. So I know I could take another one of these and switch them to ground. So I could take this transistor and I could use, if this turns on, connect, and I'm golden. I would like to also switch power with the transistor. Now, in this case, remember, it's easier to build transistors all of one type. Now, it would be better, and I will prove this in a little bit. I'm going to just take it on faith right now, and in about 10, 15, probably about 10 minutes, I will show you why this is the case. Right? PNPs are better for power. NPNs are better for ground. But it's easier to build everything all at one time. So I'm going to switch power with an NPN. Not as great for switching, but plenty good enough. Right? Because I'm not as concerned with perfect, but it will be fast. So we're going to want another NPN up here. Leave a little gap. I'll explain why this diode is here in a sec or two. All right? But this, and then this hooked up, resistor going to power. I'm just going to put high H up there. What if they're high voltage? You can do VCC and that makes you happy. This is what's called total. Right? It's kind of sounds like a weird name, but notice how you have everything stacked on top of each other. Anybody ever seen a totem star? It's a whole bunch of things stacked on top of each other, picture-wise. So, for whatever reason, this struck somebody as looking like a totem that used to be carved, so it's called totem pole. Because all the components are stacked. And the idea of this is, I'm going to want to turn this one on and hook it to ground, or turn this one on and hook it to power. Sound good? So, let me just redraw this because I need to be able to make a little table and I didn't leave myself enough room. Okay, so real quick, we've got our high, goes through a resistor, top transistor, diode, output, bottom transistor, ground. I'm going to call this A and B, and then my output C here. I'm going to make a little middle chart. I'm going to call this transistor 1 and this transistor 2. Just so we remember what's going on. And then our output C. Now, A and B, they could both be off. Right, B could be a 1. I could have 1, 0, I could have 1, 1. And again, one just high voltage. Now, assume A is a 0. Right? Well, if A is 0, this is not on, is it? Right? So what happens to T1? If A is 0, T1 is off, right? It's not conducting. How about T2? Well, T2, if B is 0, T2 is off, right? That means this is completely disconnected, right? What if A is 0? Well, we know this is off. What if B is 1? This is on, right? So what is C in that? Well, this one was C, right? It's disconnected, right? If it's off and on, if this one's on, then C is 0. But what if I've got a 1 here? That means T1 is on, right? Because it's high. So this will be less, right? This point here will be A minus 0.7, and this point will be A minus 1.4, right? So this one is off, so it's not in the picture. So this is whatever A is minus 1.4. And if I let A be 5 volts, then I've got 3.4, which is still, well, that's 3.5, so if you look at it, that gives me 3.6 as an output. TTL logic, depending on the particular version of TTL logic you have, all TTL logic, if it's above 3.5 volts, is considered true. Depending on the type of TTL logic you have, above 2.5 could be considered true. Right? So I'm still in the true zone, and that's a fine output. And this is actually why that 3.5 comes in. Right? Because it could have been a little less than 5, so you usually 3.4 or 3.5, you still call it good to allow for this zone. Okay, what if they're both 1s? Then they'd both be on, right? And now what do I have? Yeah, through a resistor, but that's not the best spot. So what's going to happen in that case? It could work because this is in essence a wire, so it's going to look like a resistor going through, right? So it would work, but in essence you've now made your same output from the other state. And this would in essence go to a 0, but we're just going to put a little I here as a note to ourselves, high current, potentially. Now, this is not ideal to what we want, right? This one, we do say this is kind of a high. I do like the idea of, really, I like this state and I like this state, right? Now, the question is, how do I get that and the other possibilities? Because I don't want Z as a high impedance. It's not my favorite, right? And if I could avoid this, I'd like to avoid this. So now what I have to do is, what if instead of a 0 or 1 here, what if we allowed this to have potentially a middle state that was on? So I could take this and I could say, well, I could allow, technically speaking, I'd be okay if this was still a 1, right? But what if I had a middle zone? And I allowed a little resistor here, and I potentially have a separator here too, but I'm going to allow another resistor here. I'm going to call this one R1. I call this one R2. And now I take one transistor here. There. Now, if I do this, right, I've got some options. This is now some new input. Let me call it D. And D will control what is A, what is B. That make sense? So I'm just kind of stepping back to figure out how. So D, which is the input to this transistor, could be a 0 or a 1. What happens if D is a 1?
D is off.
So this is connected. So that makes A and B basically equal to each other, right?
Yes.
And what value is that? So in essence, this is a wire. So I know the H here, but now I have two resistors.
So it's going to be.
What happens when you have two resistors like that? It's a voltage divider. So what's the voltage in the middle? R2 over R2 plus R1. Times whatever the high voltage is. That's what a voltage divider does, right? It's somewhere in the middle. Now what happens if D is 0?
If D is 0, A is.
This is covered, so A is.
A is.
And what happens to B?
B is off.
Right? So A is H, which is 1. B is 0. I got this exact state, don't I? We agree? That's, this state right here is this state. I would like to make this one that state. Here's the trick to it, right? Remember each of these. What voltage does A have to be for this to turn on? Well, let's add up. There's a little tiny, but not much of a resist or drop here, right? But I've got 1, 2, right? So A has to be bigger, in essence, than both of these voltage drops here, diode 1, diode 2, and whatever that gap is, whether it's on or off. Does that make sense? So for A to be on, it has to be bigger than 1.4. So I'd really like A to be less than 1.4. Right? Ideally. Now, what is B's value? In order for B to be on, B has to be bigger than 1 drop, right? So it's got to be bigger than 0.7. So is it possible to pick something? And remember, in this case, A is B. Is it possible to satisfy both of these conditions? Yeah. What if A equals B equals 1, for instance?
Yes. So
Right?
essentially, you're pitching your based on.
So that it will press down. Now here's an added bit of fun. Once I consider this, if B is above 0.7, what happens? So that voltage divider gives me an initial value above 0.7. That transistor is going to turn on, right? So what's B going to get clamped to now? 0.7 volts. Because it can't go above that because it's a diode, right? Because then it'll take as much current as you want, and it will in essence cut that other resistor out. So the net resistance will drop to basically nothing. So you cannot possibly, under this configuration, get B above 0.7. But A is equal to B.
There you go. A can be on. B can be.
Yeah. So under this configuration, B and A can't both be on at the same time. Because the second B turns on, it's going to clamp it down to 0.7, and A has to be bigger than 1.4. It can't ever do that. So B, that's the default. Transistor 2, in essence, will the voltage off what we allowed it to do. Does that make sense? Aye. If B is bigger than 0.7, this is on, which means this is 0.7, which means this is 0.7. But this has to be 1.4 to turn on. Can't do it. So all I do is I usually pick, or you would normally pick that resistor ratio to actually be slightly bigger than 1.4 initially, because it's going to get yanked down and you make sure you get up. But that I will yank it down really, really fast. So it's irrelevant. And the little bit of extra current actually lets it, the gate turn on faster. So you just want a little more flowing there. But anyway, on the safe side, you pick it here. Usually people actually pick it about 1.4 or 2, somewhere there. So they'll often pick it a little bit higher on the ratio, because once it gets above 0.7 in the middle, the diode will take it, but that gives you what you need to turn that diode on really fast. So, but now you can see exactly how I do it. Now I forced this case down here to be that. We've avoided the other two I don't like. It's not possible, and they're done. But this is this. We just make that one this. So all we do is we hook two out, and this one goes down here, and this one goes there. We put a resistor here to complete that configuration, which means I don't need one there. And that right there, if you look up, your first cut of TTL NAND gate, that's the one everybody gets you. It's that one right there. And you've now just walked through. The trick with analyzing all of these is just look at each transistor gate separately. And then just cascade the effects. Start, once you figure out each one, doesn't matter the order you figure out, right? They're either 0 or 1, right? And then just left to right combine them. And you'll actually build up anything that's in there. This is what's called punctual output. It's the most common output that's on there, because those transistors turn on really fast. They give really good power. Everything's lovely. Yay, we're happy. I got like a minute or two. I was just going to show you real quick why PNPs are good for power. And then as far as I'm concerned, I'm done with BJTs. If you consider a PNP, all right, so now we're doing something a little different. This is a PNP. Assume this is power. So this control leg controls this. That's what the arrow means. So if I put a 0 on its input, this opens wide, this goes here, and this value here goes high. This is a very low drop. That makes sense? PNP, the diode shows the control, positive to 0, flows, this is connected, so these two are equivalent. So I get really, really high. Does that make sense? If this goes to a 1, right, then nothing flows here, so nothing flows here, and it's disconnected at A to Z. So, and again, it inverts, but it gives you power transfer across. And that power is exactly dead on. Now, if I did the exact same thing, but I was trying to use an NPN, yeah, here's the problem. If I put a high here, right, which is why I need to open this up, this has to be high minus 0.7, which means you cannot get a high. That's why PNPs transfer power, because the PNP could transfer the full high voltage, whereas the NPN could only transfer high minus 0.7.
So that will go to.
Yes. And we care more about 0 because that reduces our noise. So we pick one, and it's better to have all the same type of transistor But if you're trying to actually switch power, and you're doing this to like guide a light or something, if you use all NPNs, and these are external power stuff, you will tend to lose a little bit. That it's not as efficient because it can't be. And that voltage drop has to happen inside there, so there's a little bit heat and stuff like that. So it's all around not quite as good to do this, but if it makes it cheap and small to build, well, then you live with it, right? If you're doing a one-off just to drive an output, then you don't have to do it. That makes sense why PNP, think PNP, more P's, more power. NPN, think more N's, it makes the negative, so I square. So that's the better transference. But when you're building a circuit, we built them all out the same height. It's just cheaper and so on. Good? Any questions on BJTs? If you know this, you know as much as most any engineer in your era is ever going to need to know about this. So you should be able to go through and do the little analysis where I was saying, here's the voltage ranges and whatnot. Your homework will just check that on it. It'll give you a different setup. There'll be a different number of transistors. But if you follow that same thing, just do each transistor separately, cascade them. I guarantee you it will work. So, you good? Awesome. Got questions? Let me know. Otherwise, I will see you all next